I'm actually Connor Myant from the Imperial College. So I'd like to welcome Connor. Connor, I'm so sorry that we are a little bit behind time today. I just want to introduce you to the audience very briefly. So Connor, if you want to switch and share screen, I can just get things rolling. So Connor Myant is a senior lecturer or assistant professor and group leader in the Advanced Manufacturing Group at Imperial College London in the Dyson School of Design Engineering. His research interests include design for additive manufacturing, mass customization, development of 3D printing technology, and tribology. He's currently the module leader for Solid Mechanics 2, which is a second-year core module in design for additive manufacturing, which is a third and fourth-year elective. Prior to starting his lectureship, he worked in the ICL Tribology Group, which he held a junior research fellowship studying synovial fluid lubrication of artificial articular joints. Connor Myant gained his PhD from Imperial College London in 2010 on the development of experimental techniques for investigating lubricated compliant bearing contacts. He graduated from University of Exeter in 2006 with a bachelor's degree in engineering and mechanical engineering. Connor, thank you very much for your presentation. Right, we're looking forward to that.
No worries. Can you all hear me okay?
Yes, it's perfect. I can see your shared screen. Thank you, Connor.
Brilliant. Brilliant. Excellent. All right. So we'll just jump straight in then and get started. So basically what I want to talk about for the next sort of 10, 15 minutes is a module that myself and my colleague Ajit Panasar started up around about 4 years ago. And our aim was to start a module at Imperial College that would be solely focused on additive manufacturing. And we realized that this would be the first module of its kind at Imperial College, in that although other modules might teach certain aspects of additive manufacturing, they might touch on the technology, they might touch on topology optimization or something like this, nothing really gave an entire module's focus to it. We also wanted to make the module open to all students across the Faculty of Engineering. And in order to do that, we wanted to minimize the prerequisites or the prerequisite skills that students would need to be able to do such a module. We wanted the module to focus on design for manufacture, or design for additive manufacture methodologies, rather than focusing on technology, technology specifications, requirements, and so forth. We really wanted it to have a design focus. And in a slightly sort of selfish context as well, we wanted to use the module as a way to highlight research activities and encourage undergraduates to take up final year projects, MScs or even PhDs with us on the subject of additive manufacturing. Imperial College has a very good broad research portfolio in additive manufacturing across all its faculties, multiple departments. But there isn't, until recently, a sort of solely focused group or focused network movement at Imperial College, and that's something that we wanted to tackle. So how did we go about doing this? So we ran it for the first time 3 years ago. It runs as a single term module, so that means we have a 10-week program. Because it's open to all students across the Faculty of Engineering, it goes into a particular or a special time slot in student timetables, and it's a 3-hour session every Friday morning. This means that we include a lecture and a tutorial activity within that 3 hours. It's quite a challenging thing to do in order of like keeping people's attention, making sure they're able to absorb and learn for that entire 3 hours. And it normally means that the lectures are doubled up, or they're a little bit longer than they normally would be. And then we've split the sort of curriculum into sort of 4 sections or 4 phases. And the way we've programmed this through the term, we're trying to sort of increase the complexity, be that either discussions around geometric complexity, functional complexity, or just the sort of level of science, CAD skills and so forth, that we're trying to build gradually as we go through the term. And we also split, we bookended the module with the sort of technologies as well. We wanted to give students enough time to go through the, let's say, the more design-led topics. We wanted to give them more time to absorb that and to demonstrate that within their coursework assessments rather than the technology ones. So we introduce in week 3 the first lecture on technology, which is really focused on the kind of more available technologies to students. And then at the end, we go for the slightly more industrial, larger, less available technologies. Okay. So just to run through what those sort of 4 sections are, we begin with this kind of core principles to DfAM, really just a sort of basic overview, basic introduction to what DfAM is. And we also touch upon this concept of the digital thread that I'm sure most of you are familiar with. But essentially what we're trying to set out here in these sort of 2 weeks is really what alert the students to what is different about design for additive manufacture to other manufacturing or more traditional manufacturing processes that they might be more familiar with. So it's really about alerting the students to terminologies, to systems, software, platforms, packages, and so forth that they need to be aware of, and kind of beginning them to ask the questions about what's possible, what do they need to be thinking about, what considerations should they be doing. Next, we move into the sort of technology of additive manufacturing, and we really follow the ASTM standard categories. As I said before, we introduced material extrusion and vat polymerization to them in week 3, and then we kind of leave all the rest till the final lecture of the module. The reason for that is we want them to consider those 2 types of technology in their coursework assessments. It's also the technology that we know is available to them should they wish to go and use it during the module to prototype their ideas or just to get their hands-on experience. Although we do have some of the other technologies at Imperial College, they're not openly available to students. They are more guarded pieces of research equipment and not really open to undergraduates. Okay, and then as we sort of enter into sort of second half of the module, this is where we really start to move into the more, let's say, advanced design components, and we begin with the sort of focusing on computational approaches, and we've sort of done this around 2 areas of lightweighting. So we introduce the students to topology optimization and the softwares and sort of basic theories that let's say run or back up topology optimization. And then in the second week, we go in depth into lattice structures, different types of lattice structures, when and where you might want to use them as well. In the final section, this is where we bring in those other sort of design approaches that I think are very specific or really enhanced by additive manufacturing and becoming a more popular and well-known areas of design. So this is the concepts around mass customization, personalization, and then multi-material or multifunctional design. So this is really where what we're trying to do with the students here is really get them to ask questions around value added. What can they get from additive manufacturing that they can otherwise embed into their products? And we're trying to get them to really ask those questions and see what is possible. So the main learning objectives of the module, what we want the students to be able to do by the end is apply the appropriate design for additive manufacture considerations and CAE methods to find an optimal design solution. We want the students to be able to explain a broad range of additive manufacturing parameters and technologies, and interpret, and I think this is really the key thing that we've tried to focus on throughout, is interpret analysis from the CAE, numerical, or any other sort of data that they can get their hands on into the wider context of product design development and beyond. So we also want the students to touch on not only the design of the object, but what that object is falling into. So what not only design consideration, but manufacturing considerations, business considerations. Is this part of a service provision, or is it all encapsulated into the object itself? And this sort of flow chart, this thought process, is kind of what we focus around all of the design thinking for the students. So it's about what data is available to them, what data are they acquiring, collecting. Is this just some dimensions, or is there something more available to them? Some, let's say, force, pressure, thermal, anything else that they can use to incorporate into the design decision making, part of the justification process for their design decision making. So next we move into this sort of how we use that data, how we manipulate that data to get it into a format that can be used directly into their design process. So that's the design synthesis. And then finally, we're getting the students to incorporate in the actual printing considerations and post-processing considerations as well. Okay, how do we assess students in the module? I think this is a very challenging thing and something that we've been developing over the 3 years, and we're going to continue to do so. And I'm very interested to hear other people's approaches to this, and hopefully, yeah, generate some discussion on this sort of topic area. But essentially, we do this using 2 pieces of coursework. So it's a 100% coursework assessed module, and then it's split evenly between 2. The first focuses on the sort of computational approaches, and the second on that kind of functional value added section of the course as well. Both involve a CAD and report submission, and we're really looking for the students to demonstrate not only their understanding of the core components that we touch on at the beginning of the module, but also these advanced components that we touch on in the second half of the module. And the main thing, or the main word that we use with them all the time is justify their decision making. So by articulating their justification for their design decisions, that's really what we're trying to mark on, rather than, let's say, the more subjective components or aesthetics of their design. So a little bit more information on the type, or the 2 assessments. The first one we've done for the last 2 years is we asked them to redesign a flip-flop. So a relatively easy looking product when we initially think about this, and something that is successfully manufactured already. There is a very clear mass production process for flip-flops. So we're wanting to see designs that really take advantage of additive manufacture to add value. You know, justify why you would want to 3D print a flip-flop rather than use an already very successful and well-established manufacturing process. The second assessment really focuses on the sort of the computational approaches and CAE methodologies. And the aim of this task is to help students develop and refine their computational skills. So whereas the other one might be more design thinking or a little bit more creative, this one is really focusing on that CAE analysis and skills. So what the students are asked to do, this they are asked to do a topology exercise on a simple bracket. But what you might be able to see, hopefully you can see in these images, that what we have here is a kind of a simple 3-point bracket. They're loaded or supported at one end, and then at the other end we load the bracket. But that loading point is just slightly offset from the plane of the support. So it's a little bit more complex than just a simple cantilever. There is a certain amount of torque through there as well. We further complicate the issue by asking students to incorporate a lattice domain into the design, which would be very difficult for the students to include in their topology simulations. So we're asking students to make some personal considerations to demonstrate their understanding of what impact that lattice domain would have on their topology analysis already. So we're looking at students to understand, justify and utilize the principles of the CA methods we give them. We train them up on Fusion 360, and they use the generative design package in Fusion 360 to do that analysis. We want to see how optimization methods can be used in the product design itself, and how the DfAM, including lightweighting features. So this is the lattice component as well. And again, the students, they are given an objective function to chase, but what we're asking the students to do in the report is demonstrate their understanding of each part as well. So it's not just based around a singular value that we're expecting the students to achieve. It's a little bit more complicated and nuanced than that. And throughout the module, we have a series of tutorial tasks that are designed to follow each lecture and the order of the lectures. So each tutorial task is building in complexity and directly relates to the subject matter that we have just been teaching them about. So they also have a direct support or input into the assessment tasks. So we're conscious that this is only a one-term module. It's 5 ECTS points. So I'm not totally aware of it, what every other university uses, but for Imperial College, that means it's not a huge module. It's just an average module and shouldn't burden the students with lots of work. So what we've tried to do is offload a lot of this, let's say the manual components, the orientating yourself around the softwares, these kind of things. They can do this through the tutorial tasks, and the tutorial tasks will help them build towards their final hand-in for the assessment. But they still are expected to go beyond what they've done in the tutorial to take in what they've learned, but also apply their own personal design decisions and justify those decisions. And through these tutorials as well, we do a large amount of coding. So it's a mixture of manual CAD operations and coding as well. And I think we've both felt that coding as a designer in additive manufacturing is a very important skill and something that we see is almost fundamental to the process. So just to conclude, we've completed the 3rd iteration of the module. We did this year's module was done online as a remote learning exercise, and we did feel that it suffered slightly for that, particularly the tutorial tasks and that side of the learning. In terms of prior skill or prerequisite skills, we found that basic understanding of CAD packages and stress analysis is recommended. We found that those students definitely excel just because of the short time frame required or the short time frame given for somebody to get their heads around things like a CAD software. We've also found that the prior skill level of the students has been improving year on year as additive becomes more mainstream, but the module itself still has a very large impact, positive impact on the student learning. There's still a lot more for students to learn about, I think, particularly within the computational and sort of value added and multifunctional design concepts. We've enrolled students from all across the Faculty of Engineering now, and have had a positive response across all of those programs. We started with 30 students, and we're looking at having 80 students next year. This brings certain challenges with it, and the need to scale up the assessment and how you deliver the training to the students. That needs to be scalable. We found that in-person delivery has a far greater impact, but we do use online video recordings of our sessions, prior recordings of tutorial tasks. We use that throughout the module that allows the students to do a certain level of self-paced learning. We found that to have a very positive response, particularly as some students are just quicker orientating themselves around software than others. So rather than trying to follow us at the front of a class, having that pre-recorded, that they can go through it themselves and we come around and help them, we found that that works extremely well. And I think the biggest challenge that we found is identifying an assessment that enables a wide range of outcomes. So something that you can clearly assess as being bad and something you can clearly assess as being fantastic, without that being overly subjective. Okay, and that is the end from me. So I'm happy to take any questions.
Thank you very much, Connor. Really appreciate the presentation. I think it's a very relevant topic, especially showing about your challenges, in particular about scaling up the successful program that Imperial College London really has. I think it's not just about trying to see the balance between practical skills, but also being able to use digital skills or online learning, for example. How do you actually scale it up to make it really successful? It's one of the bigger challenges. Let's have a look at some of the questions, because we won't have time. I really appreciate that. Maybe Connor, you might want to use the chat box to respond, but let's just see one of the questions that Chris has. So Chris's question says, do the students or the tutors define the criteria for success using different evaluations of design for an EM process? Where is it versus process time versus cost? How do you measure the criteria for success with regards to different evaluations of additive manufacturing?
Yeah, good question. What we've tried to stay away from is, let's say, more prescribed exam type questions or type tasks where there's a specific value outcome, right? There's a particular number that we're searching for. Instead, what we've left things deliberately open and just said to students that ultimately there isn't a wrong value, but there is poor justification. And what we want the students to be able to demonstrate is, tell us why you've made that. And if I give an example around the flip-flop challenge, there's ultimately, it's a nearly infinite design space. We've said to students that they can come up with products that are specific to a user group, that are completely conceptual, or it could be that you're coming up with a service provision. So it might not be that the design of the flip-flop has changed greatly, but it could be that they're saying, right, well, I'm going to get pressure maps of each of the user, and I'm going to interpret these pressure maps to get a better fit, more comfort, and so on. But for any one of those three, what we want is justify why 3D printing is the right process. Why does 3D printing add value? Why is it better than other manufacturing processes? Or why is it that you can't achieve this with other manufacturing processes? And it's that question that we're always searching for, and it's that identifying the value added. That's what we're always asking them to do, and that's what we're always judging them on.
So it's basically to understand the rationale throughout the process, the decision making steps that they've actually taken, why they've done that, and maybe through the feedback
Yeah,
mechanism from the tutors, they actually learn from doing it.
And I think it comes on partly onto the question that the last question was asked before my talk about, there's such a vast breadth of topics, and each one of them is could be a module in itself. You could teach an entire module on topology optimization. We could do an entire module on mass customization, or we could do an entire one on any one of the technology categories. And what we've really tried to do with this module is provide an overview of each one, try to just spark some imagination, some ideas in the students, and therefore also provide a coursework that allows them to do that, an assessment that gives them the freedom to do that as well, and that isn't too restrictive.
Basically, to give an appreciation and sense of appreciation, what the technology can do, the constraints, opportunities, the barriers, and also the creativity that people can actually utilize from this new technology or from the 7 processes involved in additive manufacturing. A little bit really multidisciplinary. You need to be able to solve science challenges, materials, and all that. Absolutely.
I think you've hit the nail on the head there. I think additive manufacturing is multidisciplinary. We need to treat it as such, and we need to teach it as such. That's one of the reasons why we've opened it up to all students across Faculty of Engineering, and not just focused on one department. I think you could do that. There's absolutely no reason why you couldn't do that. But then what you might end up doing, if I was just teaching it to aeronautical students, I might be tempted to focus more on topology optimization than I would on other aspects. Whereas we've wanted to do that kind of introductory level across the whole scope of design for additive. And it's a sort of fundamental question at the end of the day that we hope every student gets, is just, if you're only 3D printing it for the sake of it, then you shouldn't be 3D printing it. There's got to be a much greater reason that you've identified for using 3D printing.
There's a much bigger picture than that. Okay. Yeah. Thank you, Connor. Really appreciate that.
No
I'm sorry that because of time constraints, and I've got to go, Connor. There's still some questions in the chat box. Feel free to respond. But I think we really do need to move on. But Connor, once again, thank you for your time today. We really appreciate it.